everybody. So I will present with my colleague Emiliano some of our results that we got in the chair. So the chair with our three PhD students, one of them has already defended his thesis and the two others will defend it in December. So the goals of the chair is to use advanced logics and argumentation models to explain predictions of machine learning models. So our contributions are mainly on reasoning models, so it's purely symbolic AI, and then we apply those models for explainability of classifiers. So in explanation, we focused more on what we call black box models. So we don't focus on the internal structure of the classifiers, but we consider it as a black box. So we are interested by explaining either the predictions of instances or the classes in general. Okay, so what we are interested in is mainly four main questions. The first one concerns the properties that are needed by that classification model or an explanation model, should satisfy. To know the different types of explanations that we can define. To know how to persuade users by the explanations that we generate. And finally, how to generate those explanations in an efficient way. To answer these questions, we have our first contribution consisted of the theoretical foundations of explainability. The second one concerns the formal analysis of various types of explanations. The third one concerns the persuasion aspects in terms of dialogical explanations, and the last one we investigated different ways for generating efficient explanations, and we focused on one type of explanation that I will discuss later. So concerning axiomatic foundations, there are very, very few works on the topic in the literature. I didn't find works on the topic. And this axiomatic foundation concerns of studying the properties that an explanation function should satisfy. They clarify, they are important because they clarify the assumptions that which underlie an explainer. They shed light on weaknesses or strengths of an explanation model. For instance, if you have a property which is violated, so there is a weakness of the model. And they allow also to formally compare the different families or different explainers. Okay, in this presentation, I will focus on the explanation of classes, so it's global explanations. And I focus on one type of explanations, which consist of feature values. Okay, so this is just the type of data. So we proposed a set of formal properties. I will focus here on, I will comment the first and the last one because they play a crucial role, as we will see later. The success states that every function should provide an explanation for every class. And the last one concerns the global consistency of the set of explanations that we provide for the classes. What I mean by this, for instance, in this very basic example, if I have, for instance, the fact that a person is not in vacation is an explanation, for instance, for not hiking, and the function returns the fact that the person hasn't a meeting is an explanation for hiking this time. So the two explanations are consistent in the sense that we can find an instance, for instance, a person who is not on vacation and hasn't a meeting. So in this case, these two explanations shouldn't be together, shouldn't be true together. There is at least one or even both which are incorrect. Okay, so this function, such explanation model, we say that violates this property, so it's not good. Okay, so we have this. Our axioms, what we did is to characterize in a unique way the whole family of explanation models that satisfy the properties. Okay, so we have a set of the three, for instance, properties. We have feasibility and coherence representativity. They characterize in a unique way sufficient reasons. Sufficient reasons are the feature values which which lead to the prediction, okay? So we have, for instance, this is a large class. So when I say sufficient reasons, this is a large class of functions. We can define different instances of it. And one of the most known in the literature which is studied is what we call prime implicants, and they are also known abductive explanations, which are the minimal sufficient reasons. And these minimal sufficient reasons also, we have characterized them in terms of axioms. So if we add a fourth axiom, so we have this. And an important result that we got also is that from these sufficient reasons, we can generate automatically the sufficient reasons for changing a prediction. And these are what are known by contrastive explanations in the literature. So there is a duality. If you know one, you can generate the other, and vice versa. The second group of, the second family of functions that we characterize is what we call necessary reasons, which are the feature values which are whose absence leads to changing the prediction. So this family also is a large family which is characterized by these axioms, and we have also a duality results with the necessary reasons for changing predictions. These nice results, unfortunately, hold for the case where these explanations are generated from the whole feature space, because remember that in our study we completely abstract away from the internal structure of the model, okay? So what happens when, this is not reasonable, of course, to generate, for instance, an explanation from the whole feature space. So the solution was to consider a subset of the feature space, okay? But in that case, we have an impossibility result, for instance, which says that these two axioms, remember that I explained, success and coherence, cannot be true together, cannot be satisfied together if the function generates prime implicants, okay? And this shows that Lime and Encore, for instance, which are known in the literature and which generate prime implicants, they violate the property of coherence, leading that then to incorrect explanations. So these formal results, as I said, allow us to identify exactly the weaknesses and what is the exact property which is violated. Okay, so now my colleague will explain the two next contributions.
Thanks, Leila. So what we did in this section of the share. Okay, so I give you the idea and what is the mission here. So we want to develop a family of languages, formal languages for reasoning about explanation. So we take the stance of logicians. So we want to develop languages. And the kind of analysis we do in this section of the work is mostly a complexity analysis. So we develop languages, more and more expressive languages in which we can express more and more things, and then in parallel, we conduct a complexity analysis of different types of problems we can express in these languages. So most of the problems we study are satisfiability checking. So if you are a bit familiar with logic, what is satisfiability checking? You want to check whether there exists a model for your formula. And then on the other side, you have model checking. You give me the model, so the model is given, and then we want to check whether the model satisfies the formulas. So let me briefly give you some idea of the kind of languages for modeling explanations we developed. So we start with the simplest languages, which is what we call languages for modeling explanation in white box classifiers. So here the assumption is that you know the function. Okay, so that's what Leila was showing. The table is given. So you want to reason about explanations in this case. So the kind of language you could use to do this kind of reasoning is a basic modal logic where you have a single modality box. And in this very simple language, you can basically write down many types of explanation. So you have prime implicants, you have abductive explanation. So there is a way of writing down contrastive explanation and also counterfactual explanations. So this is the basic language we developed. Then the next move was to consider a more general notion of classifiers. So here you don't know the function. You have only partial information about the classifier. And so to reason about this kind of situation, you need a more expressive language. So you need two modalities. So the expressivity of the language increases. So technically, we enter into the family of products of modal logic. So the expressivity increases. And then we can write more things. So this language is more expressive. So we have a subtle distinction we can reason about here is the distinction between objective explanation. So what is an objective explanation? So as I was mentioning before, the function is given. You have the classifier in front of you. So you want to compute explanation when the function is given, while subjective explanation is explanation of a classifier while you have only partial information of it. Okay? So to write down this idea, you need this formula. So trust me. So that's the formula you can, the expression which represents this notion. And then the third kind of language we developed was languages for reasoning about counterfactual explanations. I mean, this is a concept that many people are using in machine learning nowadays. It goes back to logic. So the logic of counterfactuals goes back to the 60s. So there was a famous philosopher, David Lewis, who developed this kind of logic. So we went back to Lewis and we reactualized this machinery to reason about counterfactual explanation in classifier systems. And we developed two types of languages. So we are able to reason about relativized counterfactuals. So this is the basic operator. So in which sense is relativized? So in counterfactual explanation, you need a notion of distance. So you have a distance between two instances. And one way of computing the distance is by Hamming, the Hamming distance, okay? So X, when it's relativized, is the set of variables that are used to compute the distance. While unrelativized counterfactuals, basically you have the full range of variables which are used to compute the distance. Okay, so these are basically the languages we developed. So what is the complexity of all this stuff? Okay, so this is a table which resumes part of the complexity results we get in our work. So if you are in the simplest setting, which is the white box setting with finite fixed propositional variables, then satisfiability checking is polynomial. The same for black boxes. Now let's assume that the repository of variables is infinite, okay? Then what is complexity of satisfiability checking in the white box cases, which is the simplest modal logic, is NP complete. So basically you can use SAT to reason about explanations in white box classifiers. While in the black box case, things get very complicated. So if you want to reason about explanation when your knowledge of the classifier is only partial, then you have X time hardness for satisfiability checking, which is very bad. I mean, this is a negative result, but it's good to know about it because you know that reasoning about this kind of situation is complex and you know that you are in X time. So things are very complicated. Then we have, so I don't have time to look at we have proof theories for all these languages. And then we also have some kind of impossibility results, which shows that basically the language for reasoning about counterfactual explanation that is used extensively in machine learning, right, is not able to capture the distance-based metrics. So that's basically the theorem we have in this. This is a paper published in KR recently. So basically when you are in the infinite variable case, so your repository of information is infinite, then the language of a relativized counterfactual conditional is not expressive enough to distinguish the concrete distance-based semantics, for instance, based on Hamming, from an abstract similarity-based measure between states. So basically, the language of modal logic is not expressive enough to capture that. Okay, then this is an HKI paper. So what do we do? What did we do recently, more recently? So we said, we have classifiers. In classifier, you don't look inside the black box, right? You basically have the input layer and you have the output layer. So why not opening the box? So if you open the box, you look at the intermediate layer of the classifier,
nodes, and then you get something which is called in formal logic causal model. So we develop languages for reasoning about causality to be able to explain for instance, neural networks. And again, that's our methodology. We are interested in developing languages with more and more expressivity and to look at the complexity. So we have a family of languages for reasoning about causal necessity, interventions, then we have causal counterfactual conditionals, and in all these languages we are able to model interesting notions which are useful to compute explanations, like actual causality. We are able to model causal explanations, and then on the semantic side, the novelty here is that our semantics is rule-based, so it's very logic-based oriented. And again, we do the complexity analysis, we study satisfiability checking and model checking. Let me give just some results we have. So when you want to reason only about causal necessity, then you are you have a logic which is NP complete. So again, you can use SAT solvers to reason about this kind of concepts. So you can reason about causal explanation using SAT solvers. Then when you reason about interventions, things get a bit more complicated. I mean, that's the kind of story we have here. So we are actually implementing an algorithm for reasoning about causal explanation by using a reduction to SAT. Okay, so here, and then I will stop. So this is more on the dialogical explanation. So as I was mentioning, so what was the pipeline? We started with classifiers. Then we move into causal models. This is single agent, right? Now, why not extending all these approach to multi-agent situations? So what is the idea? So I give you only the idea, I don't give you the language. So here is the idea is that you have a classifier in the middle, and you have a group of agents, they have to explain what is going on there, right? So the example can be, suppose you have you send your application to a bank to get a loan, and then you don't get, your application is rejected. Then you ask to the, suppose the bank as an artificial agent who is replying to your request, then you ask to the agent, to the conversational agent, why was my application rejected? Then you need an explanation by the classifier. So you enter into the field of interactive explanation. So we developed a multi-agent language for dealing with this kind of scenarios. You have multi-agents, so many agents interacting by dialogue moves, speech acts, and they exchange explanations. So the language here, I mean, as you can imagine, the expressivity of this language is higher. So you get into some language for which satisfiability checking becomes p-space. So I mean, the complexity increases.
Thank you. Okay, so now I move quickly to the last part on generation of explanations. Here we focused on one type, which is abductive explanations, which are, by the way, as I showed in the previous slide, are dual to contrastive explanations. So these kind of explanations are very well known in the literature. They are very used, for instance, Encore, Lime, etc. They are used to extract this type of explanations. However, they do not take into account constraint, which are very common in data. We may have integrity constraints, dependency constraints, etc. So our first contribution consisted of adding these constraints, because getting rid of constraints lead to an exponential number of unnecessary explanations. Okay, so here we can have, as in the example, we may have superfluous explanations which are only due to the presence of the constraints. We may have redundant explanations, etc. And we may have an exponential number of redundant explanations. So what we proposed is new types of abductive explanations which take into account these explanations by considering the coverage, which means the number of the set of instances to which they apply. So we can prove that we can get rid of all these limits. We proposed different other ways of reducing the number of explanations, but I will not get into detail here. The most important thing to know is that they are very costly from a computational point of view. And this cost we have here the complexity results, which are not very good for us. So the main reason for this this high complexity is the fact that we need to explore the whole feature space. Okay, so to get rid of this problem, what is our solution? Is again to consider a data set, a subset of the feature space. Okay, so we defined new functions, and we can see now that the complexity is okay. So in polynomial time, we can test and generate explanations. We investigated now their formal properties as in the previous slide. So we have introduced, of course, novel axioms that ensure that we deal properly with constraints. And we can see that, unfortunately, the coherence property is violated. This is not surprising because of the impossibility results that I have shown in the previous slide. And here we have success which is satisfied that so coherence will be automatically violated. So in one of the PhD students that I have, we have analyzed this. We have solved this problem. We proposed an argumentation theory which for generating explanations from samples, from data set, and which satisfy the property of coherence. It's a parameterized, it's a large family of explanation functions that guarantee the coherence axiom, which integrate knowledge and which provides also dialogical explanations. I will not go into detail because I don't have time, and I have to introduce a lot of concepts which are not maybe here. Okay, thank you very much.
Thank you. So question for Emiliano, for Leila. Yes.
Okay, maybe from the beginning. On slide 14, you had these different agents. Can I imagine this as some kind of generative method where I also have the model in the loop, so trying to bring the model to learn better, or a model which has better explanations so is this part of that concept, or is this maybe a possible extension of that?
So it's very modular. So you can see the last part. I didn't have time to go into the technical details. You can see this as a multi-agent generalization of the first part. So in the first part, you have a single classifier, a neural network, and then you want to explain. So there is an external observer, which can be the designer, and then he has his language for writing down explanation, and then you want to check why a given output was produced, right? So in the multi-agent case, in the multi-agent generalization, you have a black box classifier in the middle, and you have many agents which have partial information about the classifier. So here the game is a communication game. So you might ask me, what do you know about the classifier? Then you give me information. And then based on what you tell me, I can now have a more fine-grained explanation of the classifier output, right? So do you see the idea? So so that's more or less but that's very much the conceptual framework of what they call interactive explanation. So a single classifier and many agents trying to explain it. So yeah, you can see this even from a game theoretic point of view. Here we model it from a logical point of view. Then you need a combination of this kind of logic, and then you need, that's very technical. It's logic, epistemic logic. It's logic for modeling beliefs of agents. And then, but that's very expressive stuff.
Okay, thank you. Maybe a short follow-up, just to point to something else. So the classifier itself is not in the loop with the other agents, so the classifier stays the same and is not updated, for example, based on the quality of the explanations that the other agents get.
Yeah. Okay. Let's assume the classifier. What we assume here is that the classifier is given.
Okay. Okay, thanks.
More question? No? So let's thank our speakers and